Hello everyone. This video is about error correcting codes and cryptography. In this, we mainly focus on formulating CESS problem and introduce necessary notations. Later, we describe the staircase code and universal staircase code constructions. Followed by this, we prove that these codes achieve secrecy and minimum CO and RO. Coming to CESS code, this CESS represents communication efficient secret sharing. Similar to classical threshold secret sharing scheme, CESS also encodes a secret into n shares given to n parties, such that any set of at least t parties can reconstruct the secret and less than that cannot obtain any information about the secret. In addition to this, it achieves minimum communication and read overheads when the user contacts D, which is in between T and N. Now let us look at some notations that are used in CESS coding. Basically, a secret of size k units is formed of k alpha symbols. These symbols are drawn independently and uniformly at random from finite field. And this secret is encoded using random keys into n number of shares which are denoted by W1, W2 till Wn by CESS code. And the random variable representing these shares is denoted by W and representing secret is denoted by S. So these are the notations that are used. Now let us look at some properties. The major properties are perfect secrecy, MDS, minimum CO and RO. Perfect secrecy is given by any subset of Z or less parties should not be able to get any information about the secret, whereas MDS is a user downloading T shares is able to recover the secret. And minimum CO and RO is given by a user contacting D parties where D is in between T and N is able to decode the secret by reading and downloading exactly K plus communication overhead units of information in total from all the contacted shares, where communication overhead is given by Kz by D minus Z. So there are some points that are needed to be noted from the previous discussion. That is, since the amount of information read cannot be less than the downloaded amount, the following lower bound on RO holds. That is, like the read overhead is always greater than or equal to communication overhead. And the second important point is the MDS constraint can be omitted since it is subsumed by the minimum CO and RO constraint. So with this knowledge, now we can enter into staircase code constructions. We are going to discuss two major types of constructions. One is staircase code construction for given D, whereas the other is universal staircase code construction. One achieves optimal communication and read cost for a given D, whereas the other achieves optimal cost universally for all possible values of D between T and N. Now let us look at each construction in depth. So first of all, staircase code construction for a given D. It is denoted by NKZD. This achieves optimal communication and read overheads for any given D which is in between K plus Z and N. We take alpha is equal to D minus Z. Therefore, the number of symbols in the secret will be K times D minus Z. These symbols are arranged in a matrix of dimension K into alpha. This uses Z alpha number of random keys which are partitioned into two matrices of dimension Z into K and Z into alpha minus K respectively. So after obtaining these matrices, we rearrange them in such a way that we get the dimension of the final matrix as D into alpha, which is the key ingredient for this construction. After obtaining the D into alpha dimension matrix, we multiply it with Vandermonde matrix of size n into D and obtain a resultant matrix in which each row gives us the each different share. This is called encoding. Whereas decoding is of like two parts. One is if a user contacting T is equal to K plus Z parties, he downloads all the shares of the contacted parties. Whereas if the user contacting D parties indices by I, which is subset of the set N, downloads the first K symbols from each contacted party corresponding to VI, where VI denotes the ith row of Vandermonde matrix. times transpose of matrix formed by SR1.
Universal staircase code construction. This is similar to the staircase code construction for given D. It is denoted by nkz. Here it is partitioned to h, so hd values are shown, where h equal to n minus k minus z plus 1. And same h alpha values, but we need to take a single alpha value for k alpha. We need to take the LCM of alphas. So, unlike the two matrices, here the keys are partitioned into H matrices, and these are the H matrices formed of the respective dimension Z multiplied by K alpha I minus 1, and this is the final M matrix of dimensions alpha j plus 1 into K alpha j plus 1, and the encoding and the decoding are same as the staircase code construction for given D. The main result of this topic is proving this theorem. In theorem 1, the nkzd staircase CESS code over GF of Q greater than n, satisfies the required MDS and perfect secrecy constraints for any given t between z and n, and achieves the optimal communication and read overhead CO and RO for a given d in the range of k plus z and n. And we start with the proof of the theorem 1. First, the minimum RO and CO. A user contacting D parties download the first K symbols of each party. Let I a subset of n mod I equal to D be the set of indices of the contacted parties. Then the downloaded data is given by VA of matrix transpose of S and R1, where VA is the D into D square Vandermonde matrix formed of the rows of V indexed by I, hence invertible. The user can always decode the secret by inverting the Vi, and the user only reads and downloads the KD symbols of size KD by alpha equal to KD by D minus Z units, resulting in an overhead of KD by alpha minus K equal to KD by alpha equal to KD by D minus Z, achieving the optimal CO communication overhead and RO. MDS, we prove that a user contacting T equal to K plus Z parties and downloading all their shares and reconstruct the secret. Let I is the subset of N and mod I equal to T with the set of the indices of the contact parties. The information downloaded by the user is VIM is given by VZ multiplied by the matrix of the columns SR1 and D R20. First, we show that the user can decode the entries of D and R2, and the decoder consists of the system of the equation. The Vi is the k plus z into k plus z square Vandermonde matrix formed by the first k plus z columns of Vi. Therefore, the user can always decode D and R2 because Vi is invertible. Second, we prove that the user can always decode the entries of the S and R1 and hence reconstruct the secret. By subtracting the previously decoded entries of D from Vi of matrix transpose SR1, the user obtains the Vi Mi, where the Vi is the defined above and Mi is k plus z into k matrix formed by the first k plus z rows of M1. Therefore, the user can always decode the entries of M1 because Vi is invertible. If k plus z is greater than or equal to alpha, then S is directly obtained since it is contained in M. Otherwise, M consists of the first k plus z rows of S, and the remaining rows of S are contained in D and were previously decoded. In both the cases, the user can decode all the secret symbols. Let R denote the random variable representing all the random keys. Then it is sufficient to prove that this equation. Therefore, we need to show that the given the secret S as a side information, any collection of Z shares can decode all the random keys. A collection of Z shares can be multiplied as Vz multiplied by the matrix of column SR1 and DR20. Next, the linear system obtained previously can be divided into two systems as follows. These equations, and V double dash Z is a Z into Z Vandermonde matrix consisting of the last Z columns of the Vz, and the entries of R1 can always be decoded because V double dash Z is invertible. Then the entries of D are subtracted from the second system and obtained in V dash of Z R2, where V dash Z is a Z into Z square Van Rohe matrix consisting of k plus 1 to the k plus znth columns of Vz. Hence, the R2 can also be decoded because Vz is invertible. Therefore, the condition is satisfied and the perfect secrecy is achieved.